cells differentiate differently. Make sense? So what happens to these beta amyloid peptides? I told you before that we have these hydrophobic regions. And what happens is these hydrophobic regions actually interact like this. So here's one, this pink region, with a loop that goes to this sort of turquoise region here, and then another one, the next turquoise region. So because of the hydrophobic regions in this peptide, you know exactly where they are, it causes these peptides to fold, rather than to fold into some sort of a structure, it causes them to fold into beta sheets, just like this. So this is a beta sheet. There's hydrogen bonds between here, which allow it to neutralize that stuff. But the hydrogen bonds are in that beta sheet, it folds into a sheet. And these individual peptides, they stack together. And as they stack together like that, they form a fiber. So the peptides don't fold properly. They fold into these beta sheets, they stack together, and they fold into a fiber. So this just shows sort of the same thing. Normally, this is the beta sheet thing, right? And it'll stack together like this. You can see the yellow ones. And it'll stack together and form these fibrils. And the fibrils cross each other to form fibers. And these are the fibers that are found in the amyloid plaques. They're actually fibers that are formed from aggregated beta amyloid peptide, the 142 peptide. So one thing that I didn't tell you, I want to go back because it's sort of... What's interesting is that when people who have Alzheimer's, it's generated by mutations that cause the changes in these cleaved cuts like this. But many of the mutations don't occur within the sequence, but actually adjacent to it. Right? Adjacent to it here. But because they're adjacent to that fragment, it causes these gamma secretases to act differently and to cleave differently. There's a mutation, and most of these mutations, right, the disease can be inherited. You can inherit Alzheimer's disease. Approximately 10% of people who get Alzheimer's have inherited. And there are families. There are families that are in Sweden and in Denmark. There are mutations that's called the Swedish mutation and the Dutch mutation and stuff like that occur out here. What happens is that the mutation here, right, causes this beta secretase to become really active, and it kind of outstrips the alpha. So you get more cleavage here, and you get this big guy. The mutations that occur down here, I don't remember all of them, but there's one that's called the New Zealand mutation that occurs here. What it does is it causes this somewhat promiscuous gamma secretase to cut more at the 42 rather than the 40. So all the mutations lead to the production of more of the 42. But you can get that by mutating around that piece. Okay, so here we have these fragments forming. Now, interestingly, if you look at beta amyloid, if you make it in a laboratory, and sort of look at the structure of it, it's kind of like this. It has alpha helices in it. And perhaps even a better example of this, right, is the example of prion proteins. Does anybody know the prion story? What's a prion?
It's a misfolded protein.
Misfolded protein is what?
It misfolds other proteins to make itself.
It misfolds other proteins. So it's an infectious agent. And I'll tell you about that in a minute. Prion proteins are, what do prion proteins cause?
Mad cow disease.
Mad cow disease, right? So they cause spongiform. And so the brain becomes it literally looks like a sponge because there's gaps in the brain. But anyway, the prion protein does that. But guess what? There's a prion protein that's called PR. It's not up there, but PRSC, and we all make it. We all make that prion protein. We all have prion protein. But our prion protein looks like this. That's the structure of it. It has a lot of alpha helices in it. If you look at the prion protein from the mad cow, right, then it looks like this. It has a lot of beta sheets in it. So the normal protein, the normal prion protein, the one that's found in cells, looks like this and doesn't create a problem, but this one that has the beta sheets does cause a problem. And this is rather rare. Right? Does it say that anywhere? It doesn't say that. So the conformation changes. So that rare event occurs when the native protein forms into beta sheets. But the thing that's sort of interesting is that a protein that's misfolded, this guy here, so the prion protein, can, I'm not sure what it's called, prion precursor, PRSC. Anyway, this guy here can cause a native protein to misfold. So it induces misfolding. All right? So this protein that's folded, this is the alpha helix protein. This protein in the beta sheets can actually induce this protein to misfold into beta, and then it can stack together. And once they do, right, that's the homodimer now of beta sheets, they can induce other proteins to misshape and form together, and they form these aggregates, these amyloids, and eventually they form fibers. This protein here is actually called PRSC, prion. What's SC stand for? It's not cellular. Where did they first find prions? How's that? Were they first found in made mad cow disease? Henry Prusner got the Nobel Prize. Did he find it in a mad cow? Cannibals? Kuru disease? No, that's not what they found it. Kuru disease is 1950s. That was a lot later. That was the first human stuff. It was first found in sheep, right? What's it called in sheep? Scabies. So Harry Prusner isolated prions from sheep that had scabies. Why do they call it scabies? Scratch on trees and fences and just scratch themselves, scrape themselves off. So PRSC is the one, PRSC, like this is PRP, PRSC is the scabies one. So PRSC is this guy. PRP is the precursor, that's this guy, that's the normal guy. So the precursor, this guy, that PRP, can be changed by PRSC to form another scabies guy and just stack together like that. So it's self-inducible. Okay? Why is, so what does prion stand for? I don't remember exactly, but it is proteinaceous, infectious, something or other. Right? And so what it implies is that the protein can act as an infectious agent. And if you think about that cow disease, right, that disease can be passed by, how did mad cows first get it? How did mad cows first get spun to form that? Eating what? Eating the what?
Meat was tainted with byproducts.
Wasn't tainted. So the British, right, whenever they ate their mutton, and they ate a lot of mutton, they would eat all the food, all the meat, and then they'd take anything that was left, all the offal, dry it out, grind it up, feed it to their cows. So the cows got it from eating all of the brains, essentially, from the scrapy sheep. That's where it first came from to cows. It's how mad cow. So the disease can be passed on by eating the stuff. Bottom line is, if you take prion material, if you treat it with ribonuclease, you treat it with DNA, you treat it with things that you would think would mess up all of the inheritable material, right, the DNA or the RNA, it doesn't matter if you feed it to somebody or, they'll still get scabies. You can still get it. But if you treat it with a protease, you can stop it. So the infectious agent, why is it infectious? Because if they eat something that has this in it, it can induce all your protein to do this in it. Form more of that. So it's infectious. All you have to do is eat that cow brain. You get some of this guy, and you'll induce your normal